I will introduce the next speaker. The next speaker is Vladimir Gurevich from Barefoot Networks, Intel. Vladimir is the principal engineer at Intel and the director of Intel Connectivity Education Hub. Before joining Intel, Vladimir was a technical lead at Barefoot Networks. Vladimir also worked as a technical director at Broadcom. And before that, he was a senior manager leading the software applications engineering team. He was also one of the founders and key contributors to the comprehensive engineering training program at Broadcom. He worked as a software developer at Cisco Systems before and other networking companies in Silicon Valley. Vladimir received his master's degree in applied mathematics at Moscow Institution of Radio Engineering, Electronics, and Automation. Vladimir, thank you very much for being here. I was one of his students, and it was a true pleasure to learn from Vladimir.
Thank you very much. So I'm very glad to be here. Let me try to share my screen. I will just say that I'm a little bit worried because looks like you guys already started to discuss a lot of specific applications and deployments of P4, whereas my presentation is probably a lot more at the beginner's level, but that's what Jorge told me that might be useful. So that's what I would like to talk about, really. I hope you can see my screen. Specifically, I would like to give you a brief introduction into P4, and actually before that, we'll talk about data plane programmability as well. Okay. So here's the stuff I would like to discuss. First of all, why do we need programmable switches and what we can do with them? Second, we'll talk about how to build those programmable switches, and specifically, I will say a little bit about how they are built inside. Then we'll talk about how packet processing algorithms, so-called data plane algorithms, can be expressed, and that's where we'll discuss P4 language. And then I will kind of give you some next steps if you would like to proceed into that direction. So where to get help, how to sign up, and do all kinds of interesting stuff. And hopefully we'll still have some time for questions and answers. So I will start with an interesting premise that, of course, many of you do networking, but a lot of people believe that networking is kind of done. There is very little innovation in that area. And to a certain extent, I understand why people might think about that, is because there are a lot of standardized protocols. And if all the protocols are standard, where to innovate? But in reality, there is still a lot of innovation happens. There are just somewhat different drivers there. So the nodes, of course, are connected through internet using our standard TCP/IP protocols. But what happens inside large-scale data centers or big ISPs or inside government institutions, there is still a lot of innovation going on. There are a number of drivers for that innovation. People try to build systems on the scale that they have never tried to do before. They want systems which have a lot more flexibility. That's especially true about the cloud providers. They are looking for energy efficiency, and they are trying to replace a lot of legacy protocols with the Ethernet. So there is still a lot of innovation going on, but what is true is that this innovation happens at a pretty slow pace. Why this is happening? Well, if we think about our standard computing infrastructure, then innovation happens very, very quickly. And it is available pretty much to everyone, right? So all you need to do is you need to buy some computing device, depending on what kind of projects you have. It's all available to any student at any university. You can buy a small embedded board like Raspberry Pi. You can buy a computer. You can, at the end of the day, just run a VM in the cloud. You write a program in your favorite language. It could be big program, could be small program, and that's it. You can deploy it, you can even profit. It is a very, very short development cycle with tons of tools and very well supported and understood. In the networking world, things are very different. If you want to do anything at a real speed, at the real scale, you need to go to a company, which we typically call them OEM, companies like Cisco or Arista and so on, and ask them to build a new networking device that will do whatever you want to do, how you want to organize your network. And this company will tell you that actually they would love to build you such a networking device, but they can't, because these devices use ASICs produced by companies like Broadcom and NVIDIA and so on. And so they need to ask the vendor of these ASICs to produce the ASIC that will implement your custom protocol or your custom feature. And it takes a year or two, assuming that this vendor agrees to do that. And by that time, you know, your idea went away, you probably decided to go into machine learning or something. So very, very difficult to innovate in the area of networking. Why this is happening? Well, if we look at the architecture of standard networking device, they typically contain three classes of algorithms. The data plane in the bottom, these are the fastest algorithm, which really determine the feature set and the performance of the device. Then on top sit the control plane algorithms, which populate the tables and basically give the directions to this data plane algorithms. And at the very top sit the management plane. And so while these two top layers are typically programmed using standard programming languages and executed on regular CPUs, it is the data plane which is really problematic. And as I said, unfortunately, it is the key to the whole system performance. If you cannot get things done in the data plane, they will be done very, very slowly, because modern CPUs are no match to the speeds of our modern networking interfaces. And so people who design network equipment, they experience a huge challenge, because they definitely have tons of skills and they know how to write these two upper layers. But when it comes down to implementing things at the bottom, at the data plane, implementing the algorithms which are responsible for processing each and every packet that enters the telecommunication system, up till very recently, they had a very poor set of choices. Essentially, they had to go and use fixed function ASICs, which were very fast and could do things very quickly and at high performance, but they only had a fixed set of algorithms that were basically baked into the silicon. So anytime you wanted to ask this chip to do something unusual, something non-standard, basically the chip will say no. It will point you, or the engineers will point you to a set of data sheets which explain what kind of algorithms were put into the silicon. And besides what was there, nothing could be done. So that is really the problem that I try to describe. That is what stifles the innovation. And unfortunately, there was no real way to replace this ASICs, and there is none right now. So if you look at the performance, what you can achieve using really programmable solutions like general purpose CPUs or network processors of PGAs, this performance is a lot less than what you can do in a switching ASIC. So there was really no way out. And what we decided to do, and I come from a former startup called Barefoot Networks, we figured out that this is not the right thing, that the developers should have full control of their systems, and they should be able to process packets the way they want at the same speeds that can be achieved using fixed function components. And so that led to the design of the P4 language, and also the programmable ASIC, the first programmable switching ASIC called Tofino, which supports that language. So that way, if you have an idea how you want to organize your network and you understand what kind of control and management plane you can build, you can also express the desired data plane algorithms in P4 language, load them on the ASIC, and instead of having any kind of failure, you will have an OK, and the ASIC will do exactly what you want to do. And if you think about that, that's actually a very, very typical scenario that we went through many, many times over as we were developing our digital technologies, right? So initially we had fixed function devices like, I don't know, arithmometers or stuff. And then, of course, we came up with CPUs, and we have all the high-level languages that can be compiled. And we can load these programs on the CPUs, and that looks completely normal to us nowadays, even though about 70 years ago, it was something very, very unusual and unheard of, right? Later on, there was a time for the graphical processing using GPUs. Again, for them, there's way to abstract the processing that happens in these devices. Again, this language can be compiled. It could be OpenCL, it could be CUDA, but in any case, you go from fixed function devices to programmable devices. Same thing happened a little bit earlier in the world of DSPs, of course. It is happening now in machine learning. And so the real problem was that until Barefoot kind of came along, it was not quite clear what to do with networking devices. And why? Because they have a somewhat unusual architecture, quite different from those processing units that we're describing, that I just described before. And so what we have right now, of course, is that we have a family of Tofino ASICs. Now we have 3 there already, Tofino 2, and Tofino 3. We have a language which can describe the algorithms that we run there. It's called P4. There is a compiler. If we talk about Tofino specifically, there is a compiler called BFP4C, which can compile programs written in P4 onto Tofino. And what we get as a result, there are tons of advantages, obviously. So first of all, you get full control over the features you can put into the data plane program. You can control the table scale. You can also use P4 to describe your data plane algorithms very formally. That as a result, you can also do formal verification of these algorithms. What's interesting is that by controlling how your algorithms are compiled on the platform, you can also control the energy efficiency of these algorithms. Sometimes different choices that you make in terms of how you code the algorithm can affect that energy efficiency. And a lot of big scale cloud providers now are looking at that very, very closely because the energy that their switches consume is a big part of their overall energy budget. It all obviously became a lot advantageous to the companies which produce networking equipment because now they can build a single box, same way like we don't think about that, right? But you buy a laptop computer and you can use it for all kinds of things. You can write on it, you can process photos, videos, play music, and do tons of other stuff. With switches and telecommunications equipment, up till now, it was not the case. If you wanted to buy a switch, you buy a box. It looks exact same as a box, which is a load balancer, but this is a different device. It probably has a different ASIC inside. And so people were ending up having a lot of this network equipment, which could be used only for one specific purpose. One would be a switch, another one would be a router, another one be a load balancer, a firewall, and so on. Now you can build a single piece of hardware and use it for all these things, either together or just depending on what kind of program you can load in it. Programmability also made it practical to do tracing and telemetry, because now we could control which kind of results we can export from our data plane programs, and those results would start making sense. And of course, innovation-wise, we can now implement a lot of non-standard cases. We can use the ASICs not only to do routing and switching, but we can use them to perform load balancing. We can use them to implement network caches, perform in-network computing, accelerate machine learning, and do all kinds of things that were not possible before. And there are many other advantages as well. One is very important, is that this is your program, same way how you can choose what to do it, what will be the conditions under which you release the source code. Now you can do the same thing with your data plane programs as well. And this all became reality around 2016, 2017. So, well, now you can think of this as a whole century, 5 years ago. But you could see there's a picture of two boxes. You can barely tell which one is which. One uses a fixed function ASIC inside, another one uses programmable ASIC. And in reality, the results that you can get on the programmable ASIC are even better than what you can get on a fixed function one for pretty much the same price. So now it became a reality. And already I saw in the chat that you were discussing about buying a box, probably from the same manufacturer we have this picture from. It's EdgeCore. So I'm really glad that you came to this place. Now, question is how this became possible, because for a long time, people thought that this is something that cannot be done. The common wisdom was that if you try to build a programmable device, it will be much more expensive than a comparable fixed function ones. And so I think one of the insights that we had is that if you actually try to dissect a typical switching device, you'll realize that a lot of the silicon area used by a device is not used by the switching logic. So pretty much every device you can take, about 30% of the area is spent by something that is not related to the data plane algorithm at all. It is basically connections, MACs and SerDes. And then if you look at the remaining area, most of it is spent on memory and tables, for memory which is used for tables or packet buffers and maybe TCAMs as well. And fairly a small amount of that area is used by the packet processing logic. Now, when you build be this device programmable or not programmable, really, it does not matter. You still have to have memory. And the more we go, the more people want to put memory on the device because they want the scale to be better. And the logic occupies kind of fairly fixed amount of space. And so as technology progresses, it occupies progressively less space. So even though we might need more logic overall for a programmable device, even if this 10% of logic, we increase that amount like 2x, it is still a relatively small amount overall, a very small penalty overall that we need to add to the device to make it programmable. That's why we believe these solutions are so advantageous. And so, as I said, this became a reality. So around 2016, we built our first chip that was Tofino, a 6.5 terabit device. It has 260 lanes of 25 gig SerDes, so that's basically 260 25 gig ports or 6,500 gig ports. And ultimately, in price and in power and in area, that device was equivalent to the comparable fixed function devices as well. And then in 2019, we built Barefoot Tofino 2, which has twice as much bandwidth, and the ports could now go to the speeds up to 4 gigs per second. The device also got additional capabilities, so it became smarter. And then just recently, I didn't put a slide for that, but we announced the device called Barefoot Tofino 3, Intel Tofino 3 now. that has twice as much bandwidth compared to Tofino 2. So it's 25.6 terabits per second. Okay, so let's talk about how these devices operate, what's inside. So there are a number of insights that helped us to implement those switches, design them, decide what to put inside and what not to put inside. So overall, we believe that data plane algorithms are fairly simple, and they're limited to kind of three general classes of operations. So first of all, you need to be able to manipulate packet headers. That's what we typically do in the data plane. Secondarily, we need to be able to manipulate the switch state and interface with certain external components. And I will explain what they are in about 5 minutes. The other thing we realized is that a lot of operations that are required for packet processing are easily parallelizable, both in theory and that they have to be parallelizable. Mostly, this observations comes from a very simple fact. We are processing packet headers. These headers have many fields, and usually these fields are processed fairly independently. Last thing, and that is really not our observation, that's how these systems have been built for a long time, even in the fixed function world, is that really they are built around long pipelines. So all this brought us to a notion of the so-called protocol independent switching architecture. And that is an abstract model of a packet processing inside a high-speed device that serves as a basis for P4 language as well. So this model consists of 4 key components: programmable parser, programmable match action pipeline, and programmable deparser. So the match action pipeline consists of multiple stages, and each of the stages performs the same, fundamentally the same operation. It performs a match using some packet fields or intermediate results, and then it executes an action. And then all these stages, which constitute this pipeline, are connected together with the data, with the header and metadata bus. So the difference between programmable devices and fixed function devices is that in case of fixed function devices, it's pretty much the same structure, except that all these components are fixed and the algorithms are baked into the silicon. And in case of programmable devices, they are flexible and can be programmed. So how do these pipelines work? So first of all, the packet comes to the programmable parser, which is typically expressed as a very simple finite state machine. And what this programmable parser does, it splits the beginning of the packet into individual headers and their fields. So it can extract an Ethernet header with the destination MAC address and source MAC address and the Ether type. It can extract IPv4 header and so on and so forth. And whatever it doesn't process, it doesn't extract, is the packet payload, which will be traveling separately and will not be processed. That's one of the important things that separate, for example, switches from the NICs. NICs, as the endpoints, typically receive the whole packet, then they get to the CPU, and CPU can do whatever it wants to do with the payload. Switches typically ignore the payload. And that gives us a lot of advantages. First of all, the algorithms are a lot simpler. And secondarily, we can start processing the packet while the payload is still being received. In fact, we can even, on Tofino, we can even finish processing packet headers before we receive the end of the payload. So the header fields go into this match action pipeline. And there, as I said, we perform the same operation. We perform a match, for example, we'll match the packet based on the destination MAC address or destination IP address, and we can perform an action. For example, we can set the egress port, or we can decrement a TTL. We can do a lot of things. And we can continue doing that, adding headers, removing headers, changing headers or their fields, that is, producing intermediate results for as long as however many stages we have in that pipeline. And so that is one of the bigger differences between networking devices and corresponding CPUs, because in the CPUs, you can process data for as long as you want, maybe for a second, maybe for a week. Here, the amount of time we have to process packet is very well bounded. It is basically determined by how many stages we have in this pipeline. And then once the packet gets to the very last stage, we have the last, in this case, 3 headers standing. And it goes into a device with an unusual name called deparser, which basically performs the function opposite to what the parsers do. So it takes these headers, it gets the body, the payload of the packet, and basically puts them in the right order, forms a new packet, and then sends it out for the processing. So this is the abstract model of how high-speed processing of the packets is performed. There are a couple of things that we need to be aware of. So first of all, it's like a real pipeline or conveyor. If we talk about maybe an automobile plant, so it is a feed-forward architecture. So packets always go, in this case, from left to right. They don't jump. They go through all the stages. And that's what ensures constant processing latency. The resources are typically stage local. That facilitates proper hardware design. Unlike software, where any piece of the program or any process potentially can go to any location in the memory, it is very, very, very difficult to do at high speed. So we tend to keep resources closer to the processing units. In each stage, for example, in Tofino, we have 12 of them, and Tofino 2, we have up to 20. You can perform multiple lookups, and as a result, the programs can be a lot longer than just 20 steps or however many stages we have. And the most interesting thing that every clock, we can process a single packet. So as a result, the performance of the system is very high, and I'll show you in a moment how that works. Before we go to these details, we'll just talk specifically about how match action tables operate. So because they constitute really the essence of the processing. And so if you think about match action tables, these are indeed tables, not very different from, say, Excel spreadsheets. And it is the control plane software that typically populates these tables. One difference is that they don't have like the exact rectangular form. They have one extra entry there, which signifies the default action. And I'll explain what it is in a second. So the data come in from the header and metadata bus. The device can select which specific header fields it wants to use to form a lookup key. And then this lookup key is used to perform a lookup in the table. And so obviously there could be 2 outcomes fundamentally. Either we will have a hit, and so we find the corresponding entry in the table, and so then we will use this entry that will give us the action and the action date that we want to perform this action with. Or if we have a miss, that's precisely when we use this default action and default action data. And once we have a choice, we make a choice using that little hit signal, which one of those 2 we're using. The results will go into the execution unit. They can also, the same execution unit has access to other header and metadata fields that are carried on that bus. And the results are placed back onto the same header and metadata bus. And this is a very, very important thing here, because as you could see, the input and the output of a match action table have exact same structures. This is the same bus. So we can string in together many, many tables and many, many stages for as long as we have space in silicon. That's how this works. Now, when we want to build a real device, we need to kind of go a little bit further. Typically, switches today consist of two pipelines, the ingress pipeline and the egress pipeline. That's a very standard practice because switches that, for example, need to support multicast, and that's only possible when you have two pipelines. So in case of Tofino and Tofino native architecture, we have two pipelines which look very, very similar. So both ingress and egress pipeline have all the same components. So they have the parser, ingress and egress parser. We have ingress and egress match action pipeline. We have ingress and egress deparser. And the other thing that is crucial to operation of any real-world device are the so-called fixed function components. Unfortunately, today we cannot express everything in P4, and so we need some additional components. We need packet ingress and egress components so we can get the data into the switch and out of the switch. And between ingress and egress pipelines, it's another very important fixed function device called packet replication engine. Think of it as a multicast engine, and a traffic manager, which performs packet bufferization, queuing, and scheduling. What is important is that it doesn't really matter what kind of configuration you have in your pipeline. Does it have this configuration, or it can have any kind of other shapes? What type of traffic manager and packet replication engine you can do? You can use from P4 standpoint, and we'll talk about the language in a second. They all look the same because we can control these components using the so-called intrinsic metadata, a set of well-defined variables which tell the devices what to do or put in information about what these devices have done for us. So for example, when the packet comes in, the intrinsic metadata can contain information such as ingress port or timestamp, and then output intrinsic metadata can contain a flag, whether we want to drop a packet or we want to send it to a port, and so on and so forth. So if you look at the, this again is a very abstract picture. And the other thing that is also very important, and also P4 language has facilities for that, is that in reality, many devices have specialized components. They're called externs. They can perform unusual computations, like, for example, they can compute hash, or they can produce a random number, or they can do all kinds of things that are necessary to build interesting programs. And again, the language is very flexible. So it allows us to have all kinds of different pipelines with all kinds of different components, but like a Latin alphabet, which we can use to write all kinds of different languages, which might have nothing in common. Same way P4 language allows us to describe programs which run on different hardware with completely different architectures. If we look at Tofino specifically, you will see that's pretty much how it is. So think of this as a device in its full configuration. It has 4 independent processing pipes. Think of them as like 4 CPU cores. They can all work independently. There is, of course, common logic, so we can connect the chip to the PCIe bus. There are DMA engines and so on and so forth. But ultimately, what happens is packets come in, the ports are hardwired to a particular pipe. So for example, port 0 is wired to pipe 0, and the packet is received and processed in here. And then we have a device called Traffic Manager, as I mentioned, and that is the place where packets can go from port to port or from pipe to pipe. So this device is the most complicated part of the whole chip because it has to be connected to all 4 pipes. And so it has like 4 times the performance of all the other components. That switches the packets, and then they can be processed at the egress. Overall, of course, things are a lot more complicated. So I kind of prepared a little animation that might be a little bit fun to see how packets go through the real pipeline. So this is a more technical drawing of a real pipeline of such a device. As you can see, packets enter the switch, and every clock, and Tofino operates at 1.22 gigahertz. So each pipe can process 1.22 billion packets per second. A new packet comes in. It is first received, and then after going through some technical buffers, it is parsed. We have actually 18 parsers which work on packets in parallel. Packets received from different ports can be parsed in parallel because parsing is a relatively slow operation. Unlike the match action where we can do a lot of things in parallel, for parsing you need to process packets byte by byte, so to speak. So you need a little bit more time. And then packets get into the heart of the switch, which is the match action pipeline. So in Tofino, we have 12 stages. In Tofino 2, as I said, we have 20. And that's where we perform these match action operations and decide what needs to be done with the packet. After the first pass through this match action pipeline, the packet gets into the ingress deparser. We reconstruct the new packet in the ingress packet constructor, and then it gets stored in the traffic manager, and eventually it gets queued, maybe it gets replicated prior to that. And then as you see, it goes for the next round, which is egress processing. So there it is parsed again, this time by the egress parsers. Then it goes through the match action units again. And so as you can see, it's effectively in case of Tofino, it doesn't have to be that way, but in case of Tofino, these match action units effectively act as a two-threaded device. So they process two packets independently. And then finally, the packet, we reassemble the final packet, reconstruct the full packet byte stream, and send it out to the egress. What might be interesting is for you to notice that even though we process one packet per clock, the pipeline, even on this animation, is pretty long. And so as you can imagine, at the same time, we process in here a couple of dozen packets. In reality, Tofino, a packet can take anywhere from a couple dozen to a couple hundred clocks to pass through the pipelines, which means that each pipe processes up to, I would say, 700 packets in parallel. That's one of the secrets of why these devices are so high performant, is because their pipelines are very, very long. In comparison, for example, a typical CPU pipeline is about 15 clocks. And now, of course, we need to talk about how to program these devices, how to describe data plane algorithms so that we can produce programs that are suitable for these devices. And that's, of course, where we need to talk about P4 language, and specifically P416 language. So when we started designing this language, we had a couple of specific goals. We want to build a very specialized language that will facilitate programming of these high-speed pipelines. P4 is not a general purpose language. I do not expect people to, I don't know, write music in P4 or process pictures or do any kinds of fun stuff that we typically use with other languages. It has a fairly limited application just for packet manipulation. We wanted to build a language that will allow us to program any kind of data planes. It doesn't matter what kind of protocol we want to process. So even if you want to process IP or Ethernet or any other standard protocol that you can think, in case of P4, they're all the same. It's a protocol independent language. We also try to build a language to be target independent so that it can express algorithms for a variety of devices. And because it is a programming language, obviously it will give us the field programmability. So you can write a program in P4, load it on the device, it will get its personality. Then you can write another program, load it on the same device, it will get another personality, and so on. And one of the most important things was, and I think that was one of the best decisions we ever made, is that we wanted from the beginning for this language to be a community-driven language. So there is an organization called P4.org. It's a member of Linux Foundation, a part of the ONF project, which has tons and tons of members. The membership is free. Everything is contributed under permissive Apache license. So if you'd like to contribute, and I'll mention that later again, one of the best things you can do is to join P4.org as well. So P4 language and P4, the name P4 stands for Programming Protocol Independent Packet Processors. That name came in 2013. And since then, we actually went through 2 generations of the language, or essentially 2 very different dialects. The older one that we sort of published specification 2014 is called P4.14. And then we worked on the long-term evolution of the language, which is now called P4.16. And this one is being in use for the last 5 years, and we don't see any end in sight. So that's what we are really using. It is still a fairly simple language. It has a couple of basic elements. So there's always the data types, so we can describe what kind of data we process. It has a rich expression system and various operations on the data as usual. Although, for example, some things that are not necessary for switching and can create problems like division are absent in P4, because if you have division, you always have to figure out how to process, say, divide by 0 exceptions, and we don't really want that. There is a way to express parsers, which we program as finite state machines. So it's a fairly unusual way of programming. And we have so-called controls, which look very simple, like pieces of C code, where we execute things sequentially, just same way as you would write in any familiar programming language. And so these controls are used to express both match action processing as well as deparsing. And then P4 has a couple of additional facilities that are typically not used by the ordinary users, but they allow the vendors to express the details of their specific programs. So they allow vendors to express what kind of signals their target is using to control fixed function components or interact with them, and what kind of additional components it has that are available to P4 programs to perform some specialized operations. So here I have some examples of how you can write P4 code. So here, for example, is the code that you can write in P4 to express standard headers like Ethernet or VLAN tag or IPv4 headers. And as you could see, it is a very self-explanatory description. You open any RFC, you will be able to write the headers with the same speed you probably can type. Here is an example of a parser expressed in P4. We start with a state called start. We can extract certain headers, transition to the new state. So here, for example, I transition to the state parse Ethernet, extract the Ethernet header, check the ether type. If the ether type is 8100 TPID ether type, I transition to the next state, parse VLAN tag. Otherwise, I transition to another state called parse IPv4, and so on. So again, a very, very simple set of, but powerful set of constructs allowing us to express our algorithms. Here's how we can define actions. Very simple, same, very similar to how we do it for writing, for example, functions in any other formal programming language. In this particular case, these actions, one sends the packet to a port, another one drops a packet, manipulate the so-called intrinsic metadata specific to Tofino native architecture. And then you can define a table. You can specify what kind of field you want to match on. In this case, it's IPv4 destination address, how you want to perform the match. In this case, you want to do exact match. What kind of actions are possible in the table. You can specify the size of the table. And so that is how this table sort of can be represented as an abstract picture. Same way you can define another table and use longest prefix match, a very typical match that we use for our IPv4 and IPv6 routing. And so that is a very similar table, just the key is slightly different because even though we use the same field, we use a different match kind. And here's how you can represent algorithms in P4. So you declare the resources like actions and tables, and then it's just a fairly standard piece of code where you can check if IPv4 header is valid. You try to perform a match action in IPv4 host table using exact match. If you have a miss in that table, let's do a match in the other table, which is IPv4 LPM. So this is kind of the basics. And out of these very basics, in fact, the language is not much bigger than this. You can build a lot of cool stuff. That is the most interesting things. And these are just some examples of what people done with Tofino already. So people build caches where they cache DNS addresses. They can build some security appliances, layer 4 load balancers, all kinds of different routers and switches and NAT appliances and whatnot. And again, besides just Tofino family devices, you can find NICs, which can be programmed in P4. You can find software switches and so on. So there's a lot of space for your creativity. As we say in Russian, it's only your creativity which is really the limit. So I hope I gave you a good overview. So now what I would like to do is I would like to conclude a little bit. So first of all, we discussed how these programmable packet processors, and Intel just came up with a new term called intelligent fabric processors, but it's the same. How can they enable really the innovation? And the innovation happens when you can do things at the line rate at the highest speeds possible today, which is what Intel Tofino family devices allow you to do. And of course, they come with P416 language. That's how you can program them. And the other thing that I wanted to mention is a couple of practical steps that you can take to start doing this. And I see a lot of familiar names and faces here, which is really great because I know some people took this step. So first of all, you can join Intel Connectivity Research Program. And second, you can attend Intel Connectivity Academy to learn about the devices. And then, of course, you should be able to get the hardware from a variety of vendors and start innovating. If I have a couple minutes, I wanted to just say a couple words about Intel Connectivity Research Program and Intel Connectivity Academy. So Intel Connectivity Research Program is a program which unites people from all over the world, from academic and research organizations, but not only. Some commercial organizations also join this program so that they can do joint development together with the universities. This is the link, of course, where you can find all the information. The membership is free. It is very simple click-through process how you can apply. Unfortunately, we still have a bunch of stuff under NDA, and so one of the major reasons you want to apply is so that you can get access to all the materials which are under NDA, including the software. And there are other benefits, of course, to that. So we run a very good online support forum where people ask questions and community members help them. We provide generous discounts for training. Many vendors provide discounts for equipment and the software. And also we provide free editorial service for the papers. And this is the link. If you will later on get the presentation, we publish the link to the papers. We kind of collect them, the papers that the ICRP members write and publish. This is the map of where we have the members, as you could see, all over the world, and it's more than 250 organizations today. If you think that we don't have enough of these pinpoints, if you do zoom a little bit, just in Montreal, we have 3 universities, so that's why we don't have a lot of these pinpoints because just the scale is not very high. And the other thing that I would encourage you to do, and in fact, it's also one of the requirements for membership in Intel Connectivity Research Program, is attending Intel Connectivity Academy. I am very happy to see some of my current and my former students here. It's a great way to learn about P4 and Tofino. It's not only lectures, but they're hands-on labs. And we run those hands-on labs on AWS VMs, so they are located as close to where you are as possible. So it doesn't matter if you're in South Africa or in Brazil or in Australia, we run a VM nearby. There are lots of exercises to do, and members of Intel Connectivity Research Program get academic discounts to attend Intel Connectivity Academy. And that's pretty much all I have for today. So I guess the rest I will leave for questions and answers. Thank you very much.
Thank you very much, Vladimir. If you have any question, please feel free to write in the chat window or unmute yourself.
And I see there's might be something. So question from Zaji, is there a forum with already written up scripts? I wouldn't say a forum with the already written up scripts, but there are definitely a lot of code. I didn't mention that, but we opened Tofino native architecture and our interfaces to the public. And so now most of the researchers which write code for Tofino do publish their code on GitHub, and there you can find a lot of very interesting code, and it sometimes comes with the scripts as well. Question from Tim Reiner. That's a very involved question. Some vendor devices have P4 runtime. How is that similar, different to Tofino? So Tim, what P4 runtime is, let me just go back to one of my slides. It is an API which is necessary, or it is one of the APIs that is used by the control plane to interface with the data plane, because as you see in P4 programs, which is declare the tables, but the actual contents, the actual entries in the tables need to be populated through some API. And so we call those data plane APIs. They come in a variety of forms of fashions. So initially, the community decided to settle on a API called P4 runtime. That's a kind of second generation of the API. This API, unfortunately, has a bunch of issues that makes it not very suitable for practical purposes. And so what we do instead of Barefoot, we use a different set of APIs called Barefoot Runtime Interface. Well, at Intel now, Barefoot Runtime Interface, although now I think we are working on the new version of this, which will be less specific to Barefoot. There are some technical differences between different APIs. So in case of P4 runtime, think of this as an object-oriented API. So you have a variety of objects. For example, table is an object, counters are an object, meters are an object, and so on. And each object has certain methods. So you can add an entry to a table, or you can read a counter, that sort of thing. In case of Barefoot Runtime Interface, it is a different API that we use with Tofino. We can use P4 runtime, but the problem is that P4 runtime does not have objects which are specific to Tofino. And even though that allows us to add extensions, that will pretty much make our P4 runtime code not very useful to anyone who is not familiar with those extensions. And also, it is somewhat difficult for the compiler to generate the code for any objects which it is not familiar with. So we use a slightly different API called Barefoot Runtime Interface, where everything is expressed as a table. So the table becomes the root object of the API. And then whether you want to add an entry to a table, or you want to set a new value for the counter, or you want to for example, access a register, or you want to access a multicast group, you will use exactly the same interface. You'll just manipulating a table, and all you need to know is which specific columns this table has. Come into our Intel Connectivity Academy, and I'll tell you a lot more about these APIs.
Thank you. Is there any other questions? Vladimir, I have one question. These devices are very parallel, a lot of parallelism. May you comment about that? How is the performance so much greater than a regular CPU, the dimension of parallelism?
Well, so absolutely. So one thing I mentioned, right, is that the length of the pipeline is much higher than the length of a typical CPU. So if you look at the Intel CPU, the typical pipeline length is somewhere between 12 and 15, maybe 17 clocks. Here we're talking about 500, 700 or even more clocks. So that's a huge difference in parallelism. So if you think about one pipe in Tofino, it processes 700 packets at the same time, and with 4 pipes, that's 2,800 packets. That's one way to see the difference in parallelism. The other way, if you think about that, the header and metadata bus, which connects the individual stages, like for example here. So, you know, Intel CPUs, for example, they are 64-bit CPUs. The width of this bus in Tofino 1 is 4 kilobits. So you can think of Tofino as a 4 kilobit device, which again is very different performance-wise, of course. And every clock, when we go through these match action stages and we look at these execution units, they can actually perform more than 200 operations in one clock. So that's what pretty much ensures that high performance of Tofino that is very, very different in terms of what would have happened if we tried to process these packets using regular CPUs. Of course, we have other components. For example, if we want to do LPM, longest prefix match, or if we want to do ternary match, we use TCAMs, something that is not commonly available in CPUs, and so on and so forth.
Thank you. Any questions? Any other questions? Okay, there is no more questions. So I will be posting information, a slide for those who want to join Intel Connectivity Academy. So all the information will be in our website. So thank you very much, Vladimir.
Thank you. Bye-bye.
We will have a break. It's 2:56. We will be back at 3:10, and we will have our first hands-on session. We will have an introduction to P4 and BMP2 and how to write, compile, and download P4 code to a software switch, BMP2. So we will come back again at 3:10 p.m. Eastern time.